Okay, let's start. Okay, welcome everybody to this edition of the Colloquia Patavina. I have to stay close to here. Okay, welcome to this edition of the Colloquia Patavina. Welcome everybody. I see a lot of students here. Welcome. This edition is really here for you also. Today we are very delighted to have as a guest Alfio Quarteroni. I will introduce him now very briefly. I cannot tell you everything about him because then the introduction would last at least 1 hour, but I will give you the most important details. First of all, I want to thank here the Department of Mathematics, which is the organizer here of this seminar series. I want to thank also the people from the IT and the administration. They helped us a lot in the organization of this event, and yeah, we are happy that you're all here. So let me spend a few words regarding Alfio Quarteroni. Probably most of you know him already. He's a very well-known mathematician. So the goal of this seminar series is to invite the most famous mathematicians from all over the world and get them here to Padova, or as our director would say, sono persone che devono spaccare. And I think Alfio is really one of those persons. So we are really, really happy to have him here. So let me just give you a brief introduction of his vita. So he did his, he graduated in Pavia in 1975. Then he was, for a long time, he was a researcher there till 86. And then in 86 he got his first ordinary professorship then in Brescia. He was there then for 3 years, and then he got his position where he was then really for a long time. He was an ordinary professor at the University at the Politecnico di Milano, but at the same time then at some point he got also then a professorship at Lausanne, so he had 2 professorships, and in both locations he founded and directed then really large research labs, the MOX in Milano and a second one then also in Lausanne, and then in Milano then he founded then also other companies, the MOX Software, he was also founder and director, and he earned really a lot of prizes, so the number is so large that I cannot report everything, so sorry for that. I will just give you a few numbers from this site. So he won 2 times the ERC, the advanced grant. He won 2 times then the proof of concept, also from ERC. So he was then also a plenary speaker at the International Congress of Mathematics in Madrid in 2006. He's Senior Research Fellow of the Oden Institute at the University of Texas. He was assigned and also Commendatore dell'Ordine al Merito della Repubblica Italiana. He got also the NASA Group Achievement Award in 1992. He got the SciML Outstanding Paper Prize in 2004. He got the Galileo Galilei International Prize for Science in 2015, the Bislary Prize. He held a Neuer lecture in 2017, and he's the member of a lot of academic scientific organizations. So from the Accademia Nazionale dei Lincei, the European Academy of Science, the Accademia Europea, and also the Lisbon Academy of Science. And that's just a small number. So if you're going to Google Scholar, then you will see that his paper got cited over 65,000 times. So he got H factor almost 100, I guess, in Scholar. And he's the most cited Italian mathematician. And beyond that, so he was also very active in divulgative mathematics. So he wrote 25 books. He supervised around 70 PhD students, 80 postdocs, more hundreds of master students. So he's really one of the fundamental figures here in the mathematical community in Italy, and we are very, very happy that he accepted our invitation. And so now I can only say the stage is yours, Alfio Quarteroni.
So thank you very much first for inviting me. It's a great pleasure to be back here. And it's great to have a chairman like Wolfgang, because it helps me refreshing what I've been doing in my life, and maybe it's a bit too much. I think I could have enjoyed my life much better. So, as you see, there are two keywords here. One is artificial intelligence, and the other one is fundamental science, which seem to be kind of, how to say, competitors. But this is the overall idea of my lecture. So I'm interested in solving a problem, and this is an applied problem. It could be, I called it generically physical problem. It might come from physics or engineering or from medicine or from sports, from economy. And want to solve it, and the traditional way I've been trained of is go through this branch, say, so translating it into a mathematical model, so using equations basically. Most often in my case partial differential equations, but this is not the only way, of course. And then since those equations are not solvable, typically you need to resort to an approximation. So approximating a problem means basically going from infinite dimension to finite dimension. So you produce a model, a numerical model, that you can call generically digital model, right? And you end up with a solution that you hope to be good enough or close enough to the original problem. On the other side, in recent years, we have been used to see a completely alternative approach, namely collecting data, no theory. So the left-hand branch is guided by theory, by theoretical knowledge, fundamental laws of physics, for instance. So on the other side, you have data collection, and you can divide those data into a training set of data and the testing set, and maybe a validation set, and use the training set to train typical neural network, not necessarily neural network, but say machine learning algorithm. So you develop this algorithm and you end up with a solution. So typically here what you have is an input and an output. Output means that you have a question to answer to, and input is made by data, right? So you want to extract knowledge from those data, typically. So those are two alternative approaches, very different one another. But to me, what is most interesting is trying to have these two approaches connected together. So I try to extract the best of the two and to superpose them. And this is what is today called sometimes scientific machine learning. But let me say that more generally speaking, you can think about scientific AI, so scientific artificial intelligence. This is more or less the, say, message that I would like to convey today. Having these two models interacting, these two approaches interacting, is also important to develop what is called digital twins. There's a lot of confusion on digital twins, but digital twin is, I think I will not have the time to elaborate on that, but digital twin is a virtual representation of the reality, which is in constant dialogue with the reality. And often this is done in real time. So you are really to, I don't know, control the use of a bridge, or to control an airplane which is landing on a ship, say, and controlling very complex systems in real time. So you need a digital representation of those systems, but also you need to have those systems connected with the real object and having a two-way dialogue between the two. I will not go through this because of lack of time, so I will mostly develop this part here and that part there, and then I would like to show you some example of how you can merge the two approaches in a suitable and original and effective way. And now, let me start with the left-hand branch, digital model. What does that mean, developing a numerical model? This is what is called typically computational science or scientific computing. So you have your problem and you have a mathematical problem. A mathematical model represents this solution. So instead of having you physical that you do not actually know, you have you, the solution, right? And for the student, mathematicians call the solutions U, because U stands for unknown, right? So typically you have a relationship between data and solution that you can generically present it as being f of u d equal to 0. You approximate it, so that means you introducing an approximation of both the data and the solution, so you have UH. But then you want to solve this problem with a computer because you do not have an exact solution, you don't have a closed form solution. So you need to use a computer, meaning that you need to develop suitable algorithms and coding it, and then you want to solve it. So in the end, at the end of the day, instead of having the real solution, you have this computed solution, and you hope that this error, the difference between the two, is small, right? And this is what is called validation. You want to make sure that in the end, you have something that is meaningful. And in order to have this error here small, just use triangular inequality, you have to make sure that your modeling error is small, the numerical approximation error is small, and this algorithmic error is small. So you need to be able to control all these steps. So what is important in math, in applied math, is not to provide an exact solution. This will never be the case, unless we're working with natural numbers, unless it's a counting problem, right? What is important is that to be aware that the error that we are producing can be controlled mathematically in terms of some quantities that are in our hands, right? So this is a digital model. Of course, it's theoretically basic because you start from understanding the physics and then understanding the mathematics and the analysis, say the well-posedness, and then of course you have to understand the algorithm. This is the example in order not to be too abstract, right? We want to anchor you to a specific example. And this is one of the most difficult problems that I've been solving, namely trying to have a mathematical model of the human heart. What does that mean? It means that the heart is a complex organ and you want to be able to describe its function with two purposes, basically. The first one is to help doctors to better understand the physiology, thanks to math. And the second one is to help them for developing better therapies and sometimes to optimize surgery. So you first have to understand what is going on in the heart, so understanding the physics. So you need a conceptual model where you know that you have the coexistence of the electrical field, of a mechanical deformation, or a biochemical transformation at the cellular level, of the fluid dynamics, of the valve dynamics, of the perfusion of the myocardium, thanks to the coronaries, and so on and so forth. And connecting all those things together. So it's called a multi-physics problem. A multi-scale because we have different scales in space and time, and obviously it's not linear, and it's coupled, right? So this is the conceptual model, so I have to spend a lot of time to understand what we are talking about here, and this is, at that stage is very essential to talk with doctors and to understand the basic, say, cardiology. And then, of course, you need to develop the model, which is based on representing mathematically all these physical processes. And once you have this model, you have to approximate it and extracting information or knowledge, right? And here are some examples. So now we are studying just the electrophysiology, namely the way you originate at every single, say, second of our life, an electrical field that is originated at this very point. It's called the sinusoidal node, right? So you will see this is a map of the voltage. So it propagates first to the atria and then to the ventricles, and this is the front that is propagating, right? This is something new for the doctors. The doctor knows this, right? They are used to this picture because this can be reconstructed by the engineer who is helping the doctor to making a certain surgery, right? Typically, this is a bioengineer. So they know this, and these are the isochoric line, namely those lines connect points that are electrically activated at the same time. So here we see the picture, which is dynamic, and is also quantitative, and that's very important, right? And so this is solving the electrophysiology part, which is, for mathematicians, a system of nonlinear reaction diffusion equations. This is the computation of the force, which is called the active force that is generated due to the electricity at every single cardiomyocyte. Cardiomyocytes are the basic cells of the heart, and these are in kilopascal. Then you have to let your heart deforming, so this is deformation now. You go from 0 to 2 centimeters, and the diameter is typically for an adult of the order of 8 centimeters, so it's a 25%. Deformation is a big deformation, right? And then, of course, you want to go inside and see what happens to the fluid dynamics. And here you see the solution of a global problem, the electromechanical fluid mechanical problem. And you see the valves that are opening and closing, and you see, in particular here, for an healthy adult, the velocity field and the structures that are created. These are the microvortices that are created. So for an healthy heart, this is not a turbulent flow, but is very difficult to approximate because it's a permanent transition between laminar and turbulent. So it's a very unstable kind of flow, and they have to compute it numerically using typically what are called turbulence models. So the numerical solution is a nightmare. I'm not going to insist on that because I will not have time, but just to give you an idea, to simulate one heartbeat, which takes order of 1 second, right? Physical time, it takes about 4 hours on the biggest supercomputer that we have in Italy, Galileo, in Bologna, Cineca. So this is purely physically driven, right? This is the left-hand column of my original picture. So why did we decide to use artificial intelligence? Just because we wanted to have much quicker and efficient solution of this problem. So at the very beginning, we just used artificial intelligence to reduce our computational time, but then in the course of the years, we discovered that we can do much, much better than that. So that's the way we decided to go to artificial intelligence. So what is artificial intelligence? Is a big buzzword, right? And you can look at it from very different perspectives. You take this onion, and the most external layer of the onion are the areas where now you apply artificial intelligence in a very effective way. So where you actually have a successful application of AI algorithms, so robotics, expert system, computer vision, NLP, speech recognition, and so on and so forth. Now, a machine becomes intelligent by learning. So that's why you have to develop machine learning, and we have different kinds of learning. And the engine, the mathematical engine, is not only neural network, but is most often neural network these days. In particular, deep neural networks, and of course, generative AI is a very special example of deep neural networks. So this is the picture, global picture, in a very synthetic way. Of course, I will say basically nothing about this, and there's very, very few words. Machine learning is the capability of computers to learn autonomously without being programmed, explicitly programmed. There's a very generic definition, if you wish. Now there's one which is a bit more specific, which is this one. There are very many definitions here. So we're not like in math where you have a definition and this is written in the rock. It is there forever. Those definitions, artificial intelligence, machine learning, and so on and so forth, are changing in time, which is not that strange because we're really dealing with a matter that is evolving in time. So this is one of those definitions, one that I like. A computer program is said to learn from experience C. Experience C basically means data. There is no theory here, okay? With respect to some task T, we are talking about narrow artificial intelligence. We're not yet at the level of the general artificial intelligence, AGI, right? Everybody's investing a lot of money in AGI, but till now we have restricted or narrow artificial intelligence, right? The one that moves to provide an answer to a specific task. So you have a task, you have an experience on that task, basically a set of data that we use as training set. We have a measure, P, and which is a performance measure, and we want to improve this performance if you increase your experience. So very roughly speaking, the more data you have, the better data you have, the better your answer will be. Right? So you have different keywords here. You have a task, you have data, experience, performance measure, and of course then you need a model. That's a very obvious example. It's a classification example. How do we find all these definitions for that specific example? How do we teach a machine to learn from a given picture whether this is a picture of a dog or not? You have a training set. You can get a set of images, photos, say, and you label them. So you have X at A, I, these are the picture that you have from 1 to n, and this is the label. Label is, say, 1 if this is a dog, or 0 if this is not a dog. This is our, say, supervision. You need a model which basically allows you to produce an output, 0, 1, dog or not dog, for a new picture, right? Which could be a picture of a dog, of a bird, of a flower, or whatever, right? And then you need a cost function, a performance measure. Typically, you take the sum of the squares of the errors that you make, that your model, that we still have to define, will make on the training set, plus possible regularization terms. And of course, you want to minimize this loss function in order to get the parameters that optimize the performance. So the parameters are those that are the degrees of freedom that you have to freeze in order to optimize the performance. We need an optimization algorithm, and this is a very big problem, mathematically speaking. Right? Well, there are two big problems. One is how do you choose the model, and how are you making sure that the model is good enough to represent the input-output function between the data and the solution and the output. And this goes to approximation theory. The other one is how do you minimize this loss function? This depends on W. W are the parameters. How many parameters do we have? Well, it depends on the model. In large language models, you may have million of parameters, soon billion of parameters. So we are solving an optimization problem in a multi-dimensional space, and the dimension of the space is huge. I mean, if you're a student and you try to minimize functions in 2D or 3D, you know how difficult it is, right? Especially if the function is not convex, as in this case. If you now, instead of 2D or 3D, you have 100D or 1000D or million D, it's just a nightmare. So those are mathematical problems that are very open, I have to say. So the model most often is a neural network. Neural network, for those who are completely unaware, probably the empty set here in this room, I guess. But just to fix the notation, but a neural network is a mathematical object that comprises balls here. Every ball is actually an artificial neuron. Artificial neuron is something that receives input from the nearby neurons, input under the form of data. You take a linear combination of those, quantities, and then it applies what is called an activation function, which is basically a decision function. Is this information relevant for the rest of the neurons, or is it not relevant? So you can think of a stepwise function, 0, 1, or a suitable regularization, mathematical regularization of this. And so mathematically speaking, traditional neural, artificial neural network are simple mathematical objects. Then you align them, you have different layers, and they are nurtured by the input data. This is the training set, and the solution will be here. This is the output set, right? So in the case of the picture, here you will have the pixel of your picture, and here you will have the 0, 1 conclusion. Is it a dog or is it not a dog? And here are the neurons that are making the job, actually. Of course, there's the simplest possible neural network, but it encodes basically all difficulties. You can play with activation function. So we have different kinds of activation functions. Even if I have to say that in my own experience is not that crucial, and this is not so important, the way we choose the activation function. Of course, it's better to choose an activation function which is smooth, because then you have to compute the gradient of the loss function. It's better to play with the C1 function than with, say, irregular function. But this is not the crucial. But just to have an idea mathematically, what is the problem here? Well, the problem is to approximate a function, let me call it f hat, from a finite set of samples, right? And the ingredients are the input set x and the target space y, and then we have a function that goes from the input to the output. So it's an input-output function, right? So we have a probability distribution. Sorry for the mismatch here of the notation, this is the PowerPoint. You have a loss function, a distance function that measures the error that you are making. You like to compute the expected risk, which is the integral over x cross y of dy f of x with respect to the probability measure p. Then you define a subset, which is called the hypothesis space, H, where we are looking for your model. You have a training set, and you replace the risk by a numerical approximation, typically by the average of the error that you make on the training set. So the empirical risk depends on the choice of the training set. So the cardinality of the training set as well as the training data. So ideally we like to, if we look at our picture here, we have f hat, we have the subspace. Ideally we like to compute at the arg mean of R of f for all possible f, right? In fact we want to project it, but in fact you need to use an optimization algorithm, so you'll never be able to get the exact absolute minimum. You have to stop your iteration. This is an iterative method to stop the iteration before the end, so you have yet another error. So in the end you have multiple errors that you are generating, and if you want to have a good final error, you have to account for these individual errors. This is triangle inequality. So the first error, without going into details, this is what counts. The first error is the approximation error. How good is the subspace to represent the space of all possible input-output functions? Assuming that the space of input-output function is C0, right? How good is your subspace made of neural networks to represent C0? Is it a dense space, for instance, in C0, just to make an example. The second one is called generalization error, right? And it tells us at which extent the training set represents input and output spaces in a good way, right? So it's a matter of expressivity, sometimes called expressivity, or generalization, say. And the third error is the training error, and it comes from optimization theory. So it tells us how good we are in approximating the minimum of the loss function. So if we are able to dominate all these errors, in principle, you should be able to produce a result that is good enough in the sense that that would mean that our, say, neural network in this specific case would be good enough in representing all possible input-output functions. So those are mathematical problems. There are very few answers so far to this, but this is where people are actually working. So I will skip all this because otherwise we become too technical for a colloquium. But what I would like to say is something that is not yet understood, even though we are computing, I mean, we are dealing with loss functions that are non-convex in very high dimensional spaces. It seems that overfitting is not a big deal. In general, overfitting is both in numerical analysis and statistics effect. Here, even if you go overfitting with your training set, very often you'll still be able to record a very good accurate solution. And the explanation of this behavior is not, as far as I know, is not yet completely satisfactory. So some possible conjectures, but not yet a mathematical theory. So this is good for practitioners, because very often you are forgiven even if you use a model that spends too much time in fitting the training set. Right? You know that if you study numerical analysis and you have a distribution of data and you want to use an interpolant, if you use a very high order interpolant, polynomial degree very high, you may be very good in approximating those point distributions, say, but very bad in extrapolating. Right? Extrapolation means generalizing your tool, and here we're interested in extrapolating. We want to predict, want to have our machine understanding if a picture of a dog, which was not present in the training set, is actually a dog or is not a dog. So we want your machine to be able to generalize, to extrapolate, right? And in general, the fitting works against the possibility of extrapolation. Here, most often, you are able to extrapolate, to generalize, even though you are in the regime of overfitting. So this is one of the many things that are not yet understood as far as I know. The first error is the approximation error. How good are neural networks to approximate arbitrary input-output functions, and there are several results, and these are two most, I would say, basic results that I know. One is due to Sibenko, 1989. It tells us that under suitable assumptions, say, which are now difficult to fulfill, even shallow neural network, namely neural network that only have one layer, a single layer of neuron, for every epsilon, this is the accuracy that you pretend, for every function, which is C0, this is the input-output function, there exists a suitable choice of weights, namely there exists one neural network, right, such that the error in the maximum norm is less than epsilon. So it's a kind of generalization of the Weierstrass theorem, where instead of having a subspace of polynomials of degree n, you have a subspace made of shallow neural network. That's a good result. It tells us that neural networks are create a dense subspace into C0. The same day, the same year, there is another result that was obtained completely independent, using a completely different type of argument. In this case, they use a Ham-Banach theorem, and this is due to Hornick and collaborators. And it basically ends up with the same result as before, but this is also generalized to the case where f is not a C0 function, is a function in LP. So even in LP, we have the same type of result, right, of density, say, using shallow neural network. And these results generalize also to deep neural network, namely neural network with many layers. Of course, these are not constructive results, just like Weierstrass theorem, which is not constructive. Obviously, if you're interested in applications, you like to have constructive results, namely how do we choose the neural network then? We know that there exists one neural network, but how do we choose it? And here you see the first result where you start having an indication about the number of neurons that you will need to put in your shallow neural network, and you estimate them depending upon the accuracy that you want to achieve, epsilon, the dimension of your problem, and the smoothness, the Sobolev smoothness, Sobolev regularity of your function. So in this case, the input-output function is supposed to be in this space WSP. For those who do not know, that means that derivatives up to the order S are in LP, right? Distribution of derivatives are of the order S. So the higher the regularity, the better, and that's a very good answer, right? This is what you would actually expect. So, of course, the conclusion that you draw from here, you see, is a double estimate from above and from below. So it's a strict estimate. So the larger is the number of hidden neurons, the smaller the accuracy, the better the accuracy, which is good. And for a fixed accuracy, the higher the regularity of the input-output function, the lower the number n1 of hidden neurons. So the easier it will be to compute. If you have lower number of neurons, that means that you have to spend less time, computational time. And again, the larger the input dimension B, the larger the number n1 of hidden neurons. So it's very plausible, somehow very obvious, right? But it's mathematically proven. In the case of deep neural networks, that means that you have many layers. Well, again, you want to have some constructive elements that allow you to build up your neural network. Now, let me just try to comment on the interpretation of these results. It contains too many notations. It tells us that deep neural network can represent some function that shallow neural network will not be able to represent. So that's good, right? You make more work, but you are rewarded. Deep neural network typically are more efficient than shallow neural network, in the sense that they need, globally speaking, a much lower number of non-zero weights, and with the same number of parameters, so with the same computational effort, deep neural network can represent more complex functions than shallow neural network. You might know that these machine learning algorithms have been steadily growing, and there was a kind of plateau, and after many, many years, there was a kind of breakthrough. And the breakthrough, as far as I can say, is the discovery of convolutional neural networks. I talk about 2012, so 13 years ago. And this was the very first breakthrough. The second one was the transformer, that is at the very basis of the large language models, and this is from 2017. So we're talking about a history that has 70 years of, exists since 70 years. The first definition of artificial intelligence was given in 1955, in 1955, correct? Right, so 70 years. But the explosion is very recent. I mean, it came in the last 12 to 13 years. And indeed, convolutional neural networks is one of these big breakthroughs that we actually have. There are many questions, many open questions. And here, just mentioning the names of those questions. The first one is interpretability, and the second one is explainability. Of course, the third one is reproducibility. I mean, if you're an engineer and you want to solve the problem, you have to build a bridge, right? You know that with the same input data, your response should be that one. And you repeat the same computation 2 times with the same input data, you want to have the same response, right? This is not the case here because everything is probabilistic, right? So it's not reproducible. You can prompt your LLM 2 times, right? And after, say, now and then after 1 minute, same question, same prompt, and having 2 different answers. So that's not surprising because of the construction of the algorithm. But those are a bit more embarrassing, right? Interpretability. How does a neural network come to a result? And explainability. And why? Why a neural network decided to pick up certain data in the training set and not others to produce those results? Now, the issue of interpretability and explainability in science is a bit troubling. We like to understand everything. We like to explain everything because we are scientists. In the society, it's even worse because you have a doctor now that has to convince a patient to undergo a specific operation, a surgery, but he cannot explain why. Because this was decided by a neural network that too much. Or you are a young guy and go to the bank, you want a loan for your apartment, right? And the functionary of the bank tells you, no, you do not deserve this loan. You will not get this loan. Why? Because I have a neural network that tells me that you're not deserving it. Maybe he's right. Maybe you will not deserve it, but we will not be happy, right? So this is a big issue. There's a lot of effort, mathematically speaking, to try to have a better understanding of these issues. And just to give you an example of what this does mean. So here I'm putting together 2 alternative approaches. One is least squares. So everyone in life, sooner or later, will use least squares. So easy, so obvious, so intuitive, right? And this is neural network. How can you compare least square and neural network? So least square is great until here, till the last line, right? It has very few parameters, while machine learning or neural network very many parameters. Minimization algorithm, very simple here, and here you need stochastic gradient descent algorithm of first order or second order, so they're much more, say, involved. Complexity is extremely low here. You can use your laptop or your cellular phone and you solve the least square problem, while here you need supercomputers, very often, right? And in machine learning algorithm. Interpretability, very clear here. You know the parameters of the coefficient of your, say, least square solver. You know what they mean, physically speaking, depending upon the problem. While here, you do not know the different weights of your neural network, what they actually mean, right? So, no interpretability. Reproducibility, yes, for least square, almost never there. But there is a but, see? Learnability. Well, here, if you use least square, you are driving the knowledge of your method. Assume that you have a new material or a new biological tissue, and you want to find the constitutive law of this biological tissue or of this new material, right, in material science. If you use a least square method, a priori you have to tell, your answer is to tell your least square model how to behave. Is it linear, non-linear, is it exponential, is it logarithmic, is it trigonometric? This is your own decision. But if your material will not obey that law, your solution will be silly, right? You can get a good solution in a very short time, but it will not be meaningful. Okay. Here, you are not prescribing anything. You let your neural network to extract the knowledge. And the neural network, if it's well conceived, they will tell you which kind of constitutive law you have. Not in the form of a formula, right? But in the form of input-output function. So you're not prescribing a priori the physical behavior of a certain object, of a certain process. You want your method to discover it spontaneously. So that's the learnability. And why does it do that? Well, because, you know, behind you have every single neuron, you have linear combination plus this nonlinear activation function. And then you have composition of all these tools. So you have a very strong nonlinearity. You have a very involved mathematical object that is describing this process. And this very involved mathematical object will be able to extract information by itself without being guided. I think this is a very major point. You are against, I mean, you like to have everything explainable and interpretable because you want to develop pure science and neat science, but in this case, you will be surprised by how effective these tools are. Scientific machine learning is also a way to move forward in the direction of the explainability and interpretability. And is a way, as I was telling you at the very beginning, to have, say, basic science together with artificial intelligence. Basic science, Galileo told us, right, is developed, is produced by starting from experiments, making conjecture, validating the conjecture, or coming up with, say, with a refusal of this conjecture. Once you have this conjecture valid, you have a law of nature, and then since the middle of the last century, you have numerical simulation that allows you to see what you will not be able to see on the papers. And now AI is putting a four pillar to this temple of science. You have data, many data, and you have the algorithms that are able to extract information from data. Why not seeing all those things together? So what is scientific machine learning? There are, again, many definitions. This is our definition. It's very simple, very obvious. Scientific machine learning is an interdisciplinary field, which is empowered by the synergy of physics-based computational models with machine learning algorithms for scientific and engineering applications. And there are very many ways we try to have, say, the two approaches interacting with one another. So, for instance, if you have a machine learning algorithm, you know that you have experimental data, training set, machine learning algorithm, and the solution. And this is a way to help fit with the physics-based model. Assume that you know that physical process you're dealing with, and you know the PDEs. Well, these are ways you can implement in order to help this data-driven model to be more informed about the physics, right? So in the end, you want to have machine learning algorithms that are more aware of the physical processes that are behind, less blind, more theoretically informed. Say. That's one way. Of course, if you have the other way around, namely you have, che succede? All right. Physics-based, right, where you have data, initial condition, boundary condition, material coefficients. You develop a mathematical model, you have a digital model, and then you have the solution. And how can you use AI to help this process? Even if you know the process. Talking about diffusion equation or a flowing porous media or Maxwell equations or Navier-Stokes equations, whatever, right? You know the model. But sometimes you don't have enough data. For instance, in biological applications, this is always the case. For the heart, you don't have initial conditions, you don't have boundary conditions. So you'll be stuck, right, with your mathematical model. You don't know the coefficients. You don't know the material coefficients or conducibility coefficient of a specific art, a specific person, just to make an example. Or you have missing constitutive laws. For instance, at the cardiomyocyte level, you have a microscopic level, you do not have exact laws of behavior, right? So that's why you have to surrogate this missing data by machine learning algorithms. Or, again, you want to develop reduced order models. What does that mean? Instead of solving the problem, actually this was our point of attack. Instead of solving our problem one single heartbeat in 4 hours, we like to have it in 4 seconds because we want to talk with the doctors in real time, right? So we develop reduced order models which are non-linear based on artificial neural networks. So those are examples where you see an interplay between the two things. And the results are great, just great. I mean, if this is, to me, this is just extended intelligence. I mean, I start from, maybe it's too late. It's, ancora tempo?
You have still time, no worry.
All right, okay. I thought it was a timing and not allowed. All right, no, I'm just a bit lazy. Right, so Now we are in the process where we try to formalize all those things or classify them mathematically. How can we develop scientific machine learning, so the merging of artificial intelligence algorithms and physics-based models? How can we have a kind of mathematical approach to this? How can we, mathematicians need to classify, right? They need to use definitions. Mathematicians without definitions are lost people, right? So we need to base our knowledge on definitions, right? And then we start developing from there. So these are different ways to have the two approaches working together. And in particular, I'd like to mention this one, which is the third one. It's in red because it's the newest probably, right? It's called operator learning. So I will be very short here. What we mean by operator learning? When you use machine learning algorithms based on artificial neural networks, you are basically working in finite dimensional spaces. The input space is a space of vectors, the output space is a space of vectors. Right? So go from Rn to the Rm, say. You need to build up an input-output function of this type. Can we generalize these to infinite dimensional spaces? Right? Where the input space is a space of functions, and the output space is a space of observations of functions, say. Right? Just to make an example. Assume that you have this dynamical system, dty plus L of y, was L is a spatial differential operator, and maybe you have initial condition, and you are interested in observing your y at a given time. So can I predict y at time capital T by knowing y at time 0, so by knowing the initial condition? Can I build up an input-output function of this type, which works on set of a space of function, initial condition, and on a space of observation? Maybe I'm interested in finding the drag or the lift of a wing of an airplane, depending upon the angle of attack, just to make an example, right? Or I have a heat equation and I have initial condition to observe the flux at time capital T, just to make an example. So I need to construct a resolvent operator, a solution operator that goes from the space. U is the, say, set of input function that I'm interested in observing, and Z is the observation. So I go from U, assume that U is the initial condition. I want to solve the problem, the solution of the state equation, right, depending on U, and then make an observation, which is a function of Y of U, for instance, the flux, just to make an example. Can we build a machine learning algorithm that is capable of learning this operator, say? And these are two examples, right? In the first case, I want to go from this simple diffusion equation from the diffusion coefficient, which is a function, and observing the flux on the boundary, not the normal flux on the boundary. And here the second example, where I want to go from, as I was saying before, initial condition to the observation at the final stage. These are just two examples. Of course, you can go to nonlinear problems, you go to Navier-Stokes and finding the solution depending upon the Reynolds number. So, roughly speaking, this is the space of your initial condition. This is the observation. So these are infinite dimensional space. You like to decrease this solution operator. You first project it on a finite dimensional space. You use a machine learning algorithm that provides the observation depending upon this finite dimensional space, and then you want to extend it to embed it into the original observation space. So what you are looking for is this guy here, which is the composition of different operators, right? And so you want to learn this transformation, this solution operator. And there are already many examples. I don't have the time to go through this, but if you go to, for instance, this review paper that was mentioned before, you have classification of all these methods. Let me conclude. Before conclude, let me mention some of the big issues here. And so I'm going a bit beyond mathematics. The first is the course of sustainability. Is a sustainable development this one? It's not. It's not because the amount of resources that you need to develop neural networks for challenging problems is increasing exponentially fast. So for instance, you can continue developing data center, but data center are energy wars, right? They consume electricity, they consume water, and this is not a sustainable development. So you really need to work at different levels, having a better technology for the data center, having better numerical algorithms, and so on and so forth. So one direction is what is called EDL, efficient deep learning. It's a branch that aims to accelerate the prediction speed by using what is called a lightweight deep neural network. We want to have lighter neural networks. For instance, instead of using 32 bits, using 8-bit integers. You don't need to have all these weights computed with n significant digits, because you're in an iterative process. So you want to slim the computation by basically reducing the size of every weight. This is called quantization, right? And there are several techniques that are already proposed, and some of them have already some part of, say, mathematical explanation. The other one is edge computing. Now, if you make a prompt with ChatGPT or other tools like this, of course, you know that the training has been made on in the cloud, on this big, gigantic data center, and your prompt will be analyzed in those data centers, basically. It's in real time because you have very fast bandwidth, but it's accounted for in a very remote way. Can we have edge computers, namely computers or computation that is made locally, and developing most of the computation locally? If you have an autonomous driving car, you need edge computing because you have plenty of radar, LiDAR that produce continuously, and cameras that produce continuously huge amount of data, and you want them to be analyzed locally, right, most of the time, because otherwise you'll never be able to have a real-time response in your car, braking on turning, right? And also you want to get rid of possible difficulties that you may have you see in the network. If your network does not work for some reasons, you are disconnected for 1 minute, you can make disasters if you are in a driving car, right? So that's why you develop on the local, and you want to try to create an automatic mathematical way to dispatch the computation both locally and globally. Neuromorphic computers. You know, we are still all using von Neumann computers, right? Which is based on the bit representation of information. And so using those computers since the 40s, last 40s. Now people are thinking about using neuromorphic computers that mimic the shape of the brain. So having neural networks that are more inspired to the actual neurons. You have seen before, the simplest concept of neural networks are made of collecting layers of interconnecting layers of mathematical neurons that are very simple objects. I mean, you just take linear combinations plus activation function. If you think of the complexity of a neuron, biological neuron, you may wonder why those methods are so effective by simulating neurons that are so complex, far more complex. So that's why instead of using this very simple operation, we want to use a partial differential equation that describe the activation function, so they try to better describe the physical behavior of every single neuron, for instance. Or having chips that are made by biological tissues. So having biological materials, right? Instead of having the wafers on silicon. So those are new developments. We're using spiky neural networks. Spiky neural network meaning that you have the input those are spikes, right, for our neurons. Try to have a better, say, vicinity or accuracy in describing the actual physical behavior of artificial neural networks. And of course, that's the classical question that every time I'm asked for quantum computing. Is quantum computing there to save us, to save humanity? There is a lot, as you know, there is a lot of expectation. There are gigantic investments on quantum computers. Is this a technology that is mature? Can we actually use quantum computers to solve those problems, among others? And well, there are many issues. The first one is that the technology available is still extremely limited, extremely expensive, right? It's not yet a commodity, right, as in the PC. So it's still, I mean, based on very specific environments, typically academic environments sometimes, and most often in very big enterprises. They're investing a lot of money. The operation that you can make is based on unitary transformation, because this is quantum mechanics. But when we use matrices, not all our matrices are unitary. Actually, as you know, when you use computational science, typically, if you start from, very typically, if you start from a nonlinear problem, whatever it is, you end up with a nonlinear algebraic system. If you start from a linear problem, partial differential equation, whatever, you end up with a linear system. So matrices are the very basis of our computation. And those matrices are generic matrices, and not unitary matrices, right? So how can we hammer these matrices to become unitary? How can we transform our science in a unitary science in order to comply with the basic rules of quantum computing? That's a big issue. Somebody starts calling this, that's a very big word, Schrödingerization of math, right? You want to take PDE and you want to hammer it and to become kind of Schrödinger equation. So first transformation, in order then to be able to solve these equations to using in a native way quantum computers, right? There's a lot of work to do, and it is a long way, I would say. And I think there are many challenges. And now if we just look at that, not at the technological level, but at the scientific level, we are in a university environment, right? I'm sure there will be plenty of new mathematical problems that will be stemming from this area of research. And the fact that there is a concentration of a huge amount of money on the development of quantum computing these days, I think it is easy to predict that sooner or later will be somehow, I mean, if we will have to apply for a grant, if you apply for a grant, if you don't put AI, you have much lower probability to be funded. And tomorrow, if you don't put quantum, you will have even lower probability to be funded. So I think that this is a stimulus for us, for mathematicians, for you young guys, right? To investigate those things that are very challenging and very new, let's say. Quantum computing and PDEs, yeah, and no time to go through this. We can go one at a time, but so I'm going to stop here. But there are many fundamental problems that deserve to be evaluated. I asked DAL-E to, these were my Prof, conceptual and symbolic version representing artificial intelligence enhanced by quantum and neuromorphic computer, and this is what I got. So good luck now to try to understand a bit better what is behind this. For those who are interested, there is a book that is in Italian, that's been translated in English, and there are some of the concepts that I've been explaining today in a non-technical way, if you're interested. And thank you very much.
Some comments or questions from here in the auditory, some remarks, also from the students, if you would like to ask something. That's a unique opportunity, so go ahead. Yes?
I actually have a curiosity. So you've shown...
The average student.
I was very interested. You showed us that the neural network, you have this approximation theorem, in which a neural network with a certain number of parameters would approximate basically any function up to a certain error. Now, I think the error is the same that you will get by using basically any good basis on that space of function. So, as has ever been thrown the same amount of computational power to linear methods to see whether they give comparable, or, I mean, at least theoretically they should, right?
So it's, of course, a very good question, because it allows me to say something that I didn't say, which is, however, obvious, and you don't have to be, to misunderstand this very important issue. If the answer, of course, is does not make any sense to use neural network to approximate function in an environment that you already know mathematically. More precisely, if you have a mathematical problem you know everything about, you have a PDE, you know initial condition, boundary condition, whatever, right, is well posed. You have a direct method, finite element, finite volume method, whatever you want. There is no way to beat these methods by neural networks. You have to solve a forward problem, right? In particular, the approximation issue, this is not better than what you get with linear finite elements, just to make an example. And of course, you can beat it if you use, for instance, spectral methods, high-order finite elements. So the issue is not here to compare the quality of the accuracy. The accuracy of standard methods is much superior to this accuracy. And actually, you can mathematically speaking, quantify it very precisely, which is not always the case here. The issue is that sometimes with traditional methods, you are stuck, either because you don't have data, enough data, or because you don't know part of the physics or your process. In those cases, this is an extra help. If you have to solve a reverse problem, and you use traditional methods, even though you know everything in that case, computationally speaking, this would be extremely hard task. Right? Most often, inverse problem, you know, you need to use iterative method to solve many times the forward problem. Here, you can be much faster. You are sacrificing the accuracy, to some extent, but you are solving problem that would be otherwise unsolvable. And in our case, where you do not have any idea on the structure of the solution, right? As in the example that was making for the considerably low, those methods that are strongly nonlinear, very inefficient from the computational point of view, those subspaces, which are nonlinear subspaces, are able to characterize your function, and traditional method will not be able to do it. So you don't have to, as my experience, you don't have to regard those methods as alternative to those approaches where you know you can dominate everything, right? You have to use them. That's the way we do it. We use them when we do not have enough computational resources, mathematical understanding, physical understanding for solving the traditional problem.
Any further questions? Yes.
Thank you so much for your informative talk. So I am very interested in the neuromorphology computer. So my question is about, which do you think is the next game changer of the next 50 or 100 years? Do you introduce the quantum computing and neuromorphology power computer? And I personally am interested in the quantum computing as the next game changer in the next 50 or 100 years. But neuromorphological computer is also very fascinating idea for me. So I would like to ask about your opinion. Which would be the next game?
I think they will move according to two different, say, targets. Basically, neuromorphic computing. First of all, both of them, as far as I understand, they are at a very premature stage, right? But still at the level of research development. In particular, none of them have been trained enough to guarantee the performance of the actual neural network. Having said that, neuromorphic computers is an alternative, conceptual alternative to for normal computers. Right? You don't use the same principle. Right? Basically, the silicium is replaced by biological material. And if you're thinking in terms of neural networks, the artificial neural network is replaced by something which is much more resembling the actual biological neural network. Like you have a spike, and then you have some response that is very similar to the biochemical response of the neural network. So conceptually speaking, completely different kind of thing. And this will follow a different path, right? In AI, but also not in AI. then quantum computers are, well, if you have a problem in quantum physics, of course, you know that you can better use, if you have a quantum computer, than a traditional computer, this one way. But also in machine learning algorithms, they will be much more efficient for training, theoretically speaking. Right? They're much more better for inference, right? Generalization, than these methods here. They are intrinsically parallel. And that's a big deal, because when you deal with problems with millions of degrees of freedom, having parallelism, intrinsic parallelism, is a very big help. So the technology, from the technological viewpoint, I think this will be a great breakthrough when they will be available. The others are more at the conceptual level. And the two, of course, can then, at some extent, be used together, but this is just a very long time projection.
So both are not competitive?
No, I think that these are two completely different ideas that deserve to be pushed with different purposes, even though at a certain time they may take advantage of having both together.
Okay, yes, there's another question. Yes?
Sorry, I was curious about what was your approach to like the heart stuff?
To what, sorry?
To the human heart.
Okay.
So what was your approach to the subject? Did you have to like do some medicine, chemics? Is it like a team? How does it work? Like?
Okay. So I'm an applied mathematician, right? What does that mean, being applied or pure? That's my personal interpretation. Right? It's not a matter of the math that we are using. The math is the same, of course. May need more numerical analysis than combinatorics, but this is just detail, depending upon the problem. The attitude is very different. So the approach is I start from a request, a specific question that is asked by my counterpart. It could be a doctor, it could be a geologist, it could be the coach of a soccer team, right? So I start from there. And from there I start to develop a path, a trajectory, and I'm trying to use mathematics that is helpful and functional to provide an answer to the specific question. And of course you want to generalize, right? And you want to develop new mathematics. But I mean, I'm driven by the question, by the delivery, okay? And you build the team accordingly. So first of all, you need to understand the question. To understand the question, you need to understand the basic cardiology here, just to make an example. Otherwise, you're lost, right?
So is it just the basics, or like how deep are you going into?
Depending upon the question. Sometimes you have questions that are extremely difficult. So of course you need to know the basics, right? But then sometimes you need to go a bit deeper, depending upon the type of problem you want to solve. Right? For instance, the heart. If you have a problem of a valve, it's a fluid dynamical problem, of a structural problem. If you have a problem of arrhythmia, like fibrillation of ventricular tachycardia, it's an analytical problem, so Maxwell equation, just to make an example. If you have a problem of coronaries, it's a problem of perfusion, porous media, right? So they can coexist, all those things can coexist. Which one is the most important? It depends on the question, right? So my idea is to develop a model that is comprehensive enough and large enough, so the mathematical problem of the heart that you have seen, the mathematical model, is capable of describing the complete physiology and functionality of the heart. But then, when you want to provide a specific answer to a specific question that has to see with pathology, then you have to streamline your approach. And generally, you build the team depending upon the type of question you want to address. So this applies math, to me at least.
Okay, I think if you have further questions, so we will go now downstairs to have some drinks and some food. So everybody who's interested is invited also to come. And also, yeah, you can ask them further questions also to Alfio. So let's thank him again.
Thank you.